Cool. So yeah, this is going to be a talk on V8, which is Chrome's JavaScript engine. So yeah, I guess I'll just start off with a little bit about myself first. So yeah, I am a cybersecurity undergraduate at Curtin University. I work as a security researcher at, pardon?
Oh, sorry, wrong.
Oh,
Sorry,
okay.
continue for us.
Yeah, no worries, no worries. Okay, so yeah, I work as a security researcher at Eltham, which is an IT security firm based in Melbourne, Australia. And my current research focuses are in Chrome, specifically the JavaScript engine, but hopefully more in the future. Yeah, and my Twitter's on the bottom left. It's got that symbol, like that's the pick I use everywhere. But yeah, so I guess I'll get into a little bit of an overview on what the talk is going to be about. So it's first thing I'm going to cover is some background information on browsers and sandboxing in general, specifically for modern browsers. Then I'm going to get into some internals of a couple of V8 components, specifically, I believe 3 components, because I don't have I can't cover every single component of V8. There's just way too many. It'd take days to cover all of them. So yeah, it's just a couple, and hopefully it motivates all of you guys that are watching to continue on with research into more of the components. Then I'm going to move into analysis of a vulnerability for each of them. I have 2 vulnerabilities because 2 of the components are sort of connected together. But yeah, these analyses, I guess, will be focusing on the bug hunting aspect of it, not exploitation, because I just won't have enough time to get into the exploitation side of things, because exploitation is just another beast. So yeah, finally, I'll end it off with some tips on approaching V8 research yourself, just as a getting started guide, sort of. This isn't going to be perfect. It's just the way I went about starting my research into V8. So yeah, hopefully it helps people out. Yeah, so let's just get right into it then. Starting off, let's talk about how. Wait, is this? I'll just move this out of the way. I'm not sure if that's visible. Yeah. So sorry. So let's talk about how modern browsers are composed of, like in the modern day in age. So Firefox, Chrome, Safari, and Microsoft Edge, they're all made of several processes, right? So initially you have what's known as the broker process, and this process has the most privileges. It's also called the browser process or the root process, depending on which browser you're talking about. And essentially this process creates all other target processes, and it controls what privileges the other target processes get. These target processes are considered untrusted by default because they handle untrusted user input most of the time. And these target processes can be anything. The most common ones that you may have heard of are the renderer processes, which run for each tab that you have open. So for each tab you have open, you'll have one renderer process rendering the screen. GPU processes, which the GPU and DRM processes both work with the renderer process together to output things to your screen. And the renderer process, specifically here, deals with untrusted user input, right? So JavaScript code that runs on arbitrary websites that you visit. The same with HTML and CSS, DOM elements, things of that nature. So because of their untrusted nature, all of these target processes that get created, renderer processes in this case, are all sandboxed, right? And all communication between processes and mostly between the broker process and the target processes are done through IPC, or inter-process communication. So IPC calls happen between the processes. Child processes are always sandboxed, as I explained. So I'll just show you an example of what it looks like. So I just have on my machine, I use Firefox. So Firefox, as you can see, there's multiple processes open. The process at the top that says Firefox 6 is the broker process, and all the other sub-processes that it has created are probably renderer processes, GPU processes, network processes, et cetera, right? So this is how the multi-process architecture looks like. Now, I talked about sandboxing a little bit, but what does it mean for a process to be sandboxed, right? So sandbox processes have a number of different restrictions. They cannot access the file system. They cannot perform arbitrary system calls. They cannot create more child processes. And there's a bunch of other restrictions that they have, but those are generally the most common ones. Sandboxing is implemented differently in Windows and Linux. So on Windows, you have what's known as restricted tokens, job objects, desktop objects, and integrity levels. And these are what the Windows Chromium Sandbox uses to sandbox its target processes. Whereas on Linux, you have seccomp BPF in the kernel, namespaces, setuid sandbox, SE Linux, and AppArmor. So essentially what happens is the browser process intercepts all system calls and all requests made by the sandbox processes and then handles them manually, right? So if a sandbox process makes a request or a system call that's banned or blacklisted, the browser process will just deny it and either cause the target process to crash or just not do anything, just let it know that nothing happened. Or the browser process is going to take over. It's going to do the system call or the request on behalf of the target process, and then it'll move on and it'll return the value to the target process or return whatever result it gets to the target process, so the target process can then use it. That's how target processes, even though they're sandbox, they can still do things. Otherwise, they would just not be able to do anything if they can't do any syscalls or access the file system, etc. Right? But that's as far as I'll get into sandboxing and Chrome itself, because this talk isn't about sandboxing or Chrome. It's more so about V8, right? So let's just look at why we want to attack V8 first. The end goal is to always exploit the Chrome broker process, right? Because as I said, the broker process has the most privileges. You can gain code execution in any target process, but since they're sandbox, you won't be able to get a shell, you won't be able to access the file system. It's just useless, right? But what we do know is that the target process can talk to the broker process through IPC. The target process can also make some syscalls, so to the kernel, it can talk to the kernel in that way. And if you can find a vulnerability in those syscalls, you can also attack the kernel after you exploit a target process. So the general gist of things here is that you need multiple vulnerabilities to actually gain code execution or gain enough code execution where you have a shell on another machine. So usually the process or the target process that gets attacked first is the renderer process, because of how exposed it is and how easy it is to gain primitives through JavaScript, right? Because JavaScript is it's a whole language by itself. You can do heap sprays by creating new objects. You can just read from memory, write to memory. It's just with JavaScript, you can do a lot of different things. And the renderer process just happens to be one of the most exposed ones. All you need to do is host your JavaScript code on a website and get your victim to visit your website, and that's it. You can pwn them if you have a vulnerability. So V8 is, as I said, Chrome's JavaScript engine, and it runs within every single renderer process. The enormous complexity of V8 means that it contains entirely new and unique vulnerability classes. This is something that was put on the description of the talk before on AirGap's website. Yeah, generally speaking, you'll see one vulnerability that I'll analyze, the second one more specifically, that is a whole vulnerability class by itself, and I think that's really cool. So yeah, we'll look at that when we get to it, right? Before we get on to it, though, I have to explain some internals about the V8 heap and how V8 deals with objects and values within the heap, right? So the V8 heap is a compressed heap in x86-64. I don't know about any of the other architectures because I've done my research on x86-64, so I'm not going to comment on those. But essentially what a compressed heap means is that all pointers are stored as 32-bit addresses. Now, you might be wondering, how is that possible? Because in 64-bit architectures, the address space is also going to be 64-bit, right? So V8 does this pretty well, actually. So the way they do it is they store the base address of the heap memory region within the R13 register, and they call this register the root register, right? So it just stores the root address of the heap. Now, anytime a pointer needs to be dereferenced, since the pointers are 32-bit, what they do is they get that base address out of the root register, add it to the pointer, and then dereference it. Now, this might seem like it's useless, but it's actually not. V8 or Google themselves have made a bunch of blog posts, actually 2 blog posts, detailing how they've done this and how much performance improvement they've gotten. So this is how V8 heap actually works. So let's look at how values and objects are represented within the heap, right? So V8 uses a technique called pointer tagging to distinguish between heap pointers and small integers. These are the only 2 types of values you'll see within the heap directly. You might see floats like 64-bit doubles within arrays, for example, but within the heap directly, you only ever have either pointers or small integers. So these two types of, these are the two types of representations. So a small integer is called a SME in V8 terminology, and the heap pointer is called a heap object, right? So what they look like in memory, you can find this in the source objects.h header file within V8. Essentially, a SME is going to be a 31-bit signed integer followed by a 0, and a heap object is going to be a 32-bit direct pointer, which is 4-byte aligned. So the last bit, if a memory address is 4-byte aligned, the last bit will always be 0 no matter what. Because of this, a heap object's last bit is used to denote that it's a heap object by setting it to 1, right? So you can see in the comment there, the bottom line, it says, it's a 32-bit direct pointer with the last bit set to 1. So yeah, so just to clarify again, to know the difference between a SME and a heap object, all you have to do is then look at the last bit of whatever value you find on the heap. If it's a 0, it's a SME. If it's a 1, it's a pointer. So this is how V8 distinguishes between these two types of values. Now we'll get right into what a V8 sort of pipeline looks like, I guess. So the V8 pipeline sort of works like this, right? We take your JavaScript, you parse it, turn it to an abstract syntax tree, generate bytecode for it, and then it runs, right? And while it runs, V8, or more specifically, its optimizing JIT compiler, gets type feedback for speculative optimizations. So with type feedback, what it does is it makes assumptions regarding what types it's seen. And it has to do this because, again, JavaScript is not a typed language. So there are no types in JavaScript. Well, there are, but technically there aren't, right? So it gains this feedback from multiple executions of functions. And then it uses the feedback to optimize or to produce optimized machine code, which runs way faster, right? So that's how essentially the pipeline works. And in this specific case, or in this talk, I guess, I'm only going to cover the parser, and actually I'm going to cover all of it anyway. So yeah, we'll just get right into it. So to start off with the parser, right? So with the parser, what happens is initially your JavaScript code comes in from the network as UTF-8 encoded text. This parser stream converts this to UTF-16 encoded text. And the reason it does this is because UTF-16 is easier to deal with when tokenizing. I don't know exactly why, but that's what it does. This UTF-16 code text is then sent to the parser scanner, and the scanner is going to tokenize this code, right? The tokens that the scanner produces is initially sent to the preparser, and the preparser does what's called lazy parsing. So lazy parsing is essentially where the preparser skips over all functions. It skips over them, but it does make sure that the functions themselves are syntactically valid, and it stores some information for the parser later on to have an easier time parsing the functions themselves. The parser, on the other hand, will simply there's a typo in the slide. Well, it'll convert this code into an abstract syntax tree. The parser might also parse functions that were previously pre-parsed if they are now required to run. So essentially what the pre-parser is doing here is reducing the time between parsing to execution, right? So if a function is not immediately being run, there's no reason to parse it, right? You can skip past it until it's actually needing to run. That's when you can parse it. So yeah, this speeds up execution of the engine by a lot, apparently. So next, with the abstract syntax tree created, it gets passed into Ignition, which is V8's bytecode compiler / interpreter. It's both, which it's a little confusing because it has the same name, but either way, the Ignition compiler first compiles this AST into bytecode, and the Ignition interpreter then executes this bytecode. And before we move on to how the Ignition interpreter / compiler work, I'm going to actually look at a vulnerability that was found within the parser itself. And I think this is important because the parser is, again, it's the first line of defense, if you will, within the engine. It's the first place any code goes. And because of this, a lot of people think, well, parser bugs have been found already. It's going to be hard to find any new parser bugs. And so no one looks at it, right? It's just the classic, everyone's supposed to be looking at it, therefore no one's looking at it. So this is a vulnerability from late 2019 found by Dimitri Forni of Blue Frost Security. It's just a simple integer overflow. This isn't a unique vulnerability class. That's for the next vulnerability. But I just wanted to show this just to showcase that even though this is a parser, it's the first thing that anyone might look at. No one actually looks at it because this vulnerability is very easy to spot. So at the beginning, what happens is the scan method starts off by calling scanner scan single token to read in a single token from whatever JavaScript code you have, from the the UTF-16 encoded text code that you have. This scan single token has a lot of different cases that it has to handle. So in this vulnerabilities case, the vulnerability lies in the case that handles strings. So with a string, for example, it might read a starting double quote or a single quote. And what it would do is it would continuously read text until it finds an ending double quote or single quote, right? So taking the string as an example, we get the following sort of call stack. So scan calls scan single token, which calls scan string, which ends up calling add literal char. So each character of the string in a loop, right? So it calls this function in a loop, and this function calls literal buffers add char, which in turn calls literal buffers add 2 byte char. This isn't important. This call stack isn't important, but add 2 byte char is important. So within add 2 byte char, we have this set of code, and this code is basically reading each byte or every 2 bytes from the UTF-16 encoded code, which translates to 1 character. And it stores this these 2 bytes within a backing store, right? So the arrows point to the line where the backing store is being expanded when it doesn't have enough space to store more characters, right? So when the backing store needs to be expanded for more characters, because again the string can have an arbitrary length, right? It can have an arbitrary number of characters. If the backing store needs to be expanded, it makes a call to this function called expand buffer. Now, what expand buffer does is it initially creates a new vector, and this vector isn't actually C++'s standard library vector. It's a vector created specifically for V8. This vector is going to, or this new vector is going to have a capacity equal to a function called new capacity, or the return value of a function called new capacity with its argument set to k initial capacity. Now, k initial capacity is equal to 16. So when new capacity is called, what's going to happen is within new capacity, you can see when it's trying to calculate new capacity, it's going to pick the minimum between the left, which is capacity multiplied by k growth factor, or the right, which is capacity plus max k max growth. Now, capacity before this, in the second line, is set to either min capacity or the length of the backing store, whichever is greater. Now, in our case, let's just say that the string is greater than length 16, right? If the string is greater than length 16, it means we have control over the capacity variable. And because we know that capacity is an integer, it's a signed integer, so its maximum value can be 2 to the power 31 take 1, we can cause this to overflow. And when or this multiplication, more specifically, to overflow and be, even though it would be greater than capacity plus k max growth in this case, the overflow would make it so that it's less, right? And so what would happen? What happens if capacity multiplied by k growth factor overflows and becomes less than k max, capacity plus k max growth? Well, in order to understand this, we have to look at how this vector gets created. And without going into too much detail, I'm just going to show you the length function of the vector. Within the length function, it does a max length check. And in the max length check, it makes sure that the length of the vector cannot exceed the maximum limit of a signed integer, which again is 2 to the power 31 take 1. So if, for example, in our previous code, if the value overflows and new capacity becomes a negative number, the negative number would still be technically greater than an unsigned integer that is whose max value is 2 to the power 31 take 1, right? So that is why when you do this, what might happen is, well, I'll get into the proof of concept right now, actually, because that explains it. So in the proof of concept, essentially what happens is S is a string that gets created from a 2-byte string of 2 A's, or hex 4141, which is just 2 A's, repeated hex whatever that many times, right? When that happens, you can see capacity is going to equal 2 multiplied by whatever that number is, which gives you whatever that number is there, hex 2000002. So when this happens, capacity multiplied by k growth factor is going to be hex 20002 multiplied by 4, which gives you hex 80008. While capacity plus k max growth is going to be hex 20002 plus 1024 times 1024, which equals a value much less than capacity multiplied by k growth factor. But the max value of a 32-bit signed integer is 2 to the power 31 take 1, which is hex 7 FFFFFF. Now, hex 8000008 is obviously greater than that, so it's going to overflow and become a number that's smaller. When this happens, it yields a smaller value than the original capacity. And what this is going to do in the previous code, when the new vector is created, the new vector's capacity is going to be smaller than the old vector's capacity. When this happens, the mem copy in the second line or the third line of the top code block is going to copy more bytes into the new buffer than it can store, which leads into a heap overflow. And this heap overflow is, again, it's very, I'm not going to say it's easy to exploit because you still have to find the primitives. But luckily, because it's V8 and it's complex as shit, there's a lot of different objects that you can allocate. There's a lot of different things you can allocate on the heap. And that gives you access to function pointers, variables, or just normal pointers to leak memory through. It's just, you can do a lot of different things in this specific case. So yeah, this vulnerability would easily be exploitable. You can easily just gain execution or code execution within the browser process, or sorry, the target process, which is the renderer process, although it's sandbox, right? But yeah, I just wanted to showcase this vulnerability because, as you can see, the integer overflow here is very easy to spot. It's just capacity, which is a controlled variable, being multiplied and compared with capacity added with another variable. Like it's just right there. Anyone could have read this code and spotted it, but no one does, except apparently this guy from Blue Frost Security who found it. So yeah, that's the vulnerability. I'll just move on from this now, and we'll have a look at how Ignition executes the bytecode that it generates, right? So Ignition is V8's fast, low-level register-based interpreter. It takes the abstract syntax tree generated by the parser and compiles it into V8 unique bytecode. Ignition has a number of different registers that all bytecodes will explicitly use as inputs and outputs, and you'll see what this means in the next set of slides. A special register known as the accumulator register is used for calculations and return values. And this is similar to RAX in x86-64. I missed the 64 there, but yeah. So this is how Ignition bytecode generally works. So let's have a look at an example of how bytecode execution looks like. So on the top left, we have a function. It's in JavaScript. It's an add function. It has two parameters, x and y, and it just adds them together and returns the value, right? And at the end, we have to make a call to the function because of the lazy parsing thing that I explained. If we don't make a call to it, no bytecode gets generated. So yeah, so we have this on the right, we call V8, which is V8's REPL, I guess, with the --print bytecode flag, right? And when this happens, we see that the bytecode that's generated by V8 is just 4 separate bytecodes. So let's get straight into it. Wow, okay. My slides are stuffed a little bit. I'll just explain it without the red boxes. So the stack check at the beginning will check the stack pointer against a upper limit. It's going to make sure that the stack pointer is less than that upper limit to prevent stack overflows from occurring, from reaching the max recursion depth or things like that. Next, actually, I'll just use these just so you know where it's pointing, I guess. The next instruction, LDAR-A1. The A1 in this case refers to argument 1. So in our functions case, we have argument 0 and argument 1, whereas argument 0 is x and argument 1 is y. So this will load the value of argument 1 into the accumulator register, right? So that's what LDAR stands for. So in our example function calls case, this will load the value 2 into the accumulator register. The next thing, add A0, the next bytecode, add A0 square bracket 0 is going to initially, just with add A0, it's going to add the value of A0 to the value of whatever's in the accumulator register and then store the result back into the accumulator register, right? So in our case, it's going to take the value 1 for x. It's going to add it to whatever is in the accumulator register, which is 2 from y, and it's going to store the result 3 back into the accumulator register. The square bracket 0 square bracket here is interesting. This is a slot into this specific function's inline cache, which we're going to look into in the next section. So the inline cache essentially stores information regarding what this function is doing right now, which is going to be used for further optimizations later on. And I'll just skip explaining this right now because I'll explain this in a little bit. Finally, the return statement just returns whatever value is within the the accumulator register at that point in time, which would be the value 3. So yeah, I would explain, or I would go through a vulnerability for ignition specifically, but I can't, because ignition is very closely related to its cousin, I guess, which is turbofan. And they essentially run together, right? So you can see on the diagram on the right, I'll explain what that's doing. But essentially, turbofan is V8's optimizing JIT compiler, right? So when a function is ran several times, it becomes hot, according to V8 terminology. So what happens is, on the right, you can see the interpreter creates bytecode, and you can see an arrow going through the middle, and it goes plus profiling data to the optimizing compiler. So what profiling data is when the function, or when any function runs several times, the profiling data essentially says, okay, this function is being ran with this specific type of variable, or these sets of types of variables. So the optimizing compiler can then use this data to speculate that this function only deals with that certain type of value, right? It uses this profiling information and type feedback, whatever you want to call it, to just make an assumption that, okay, this function is being called with this specific type, nothing else. Therefore, I will produce highly optimized machine code that deals with this specific type, right? And again, this is important because in JavaScript, if you just have a look at that add function that I was talking about, x and y in that case was just 1 and 2, which are SMEs, right? Small integers. However, in JavaScript, x and y's can be strings, they can be objects, they can be arrays, they can be floating point values, which are different to small integers. So they can be a lot of different things. So JavaScript by default would have to check against all of those types before adding them together, right? Because adding between different types wouldn't work, and the addition between strings is, for example, different to the addition between integers. So sorry, yeah, I just lost myself a little bit. But yeah, so this is how it would make an assumption that this function is dealing with a specific type, and it would generate highly optimized machine code for that specific type. However, it also inserts checks, right? So if at any time these assumptions fail to hold true, the code is de-optimized and execution goes back straight to the interpreter. So you can see that on the right side of the diagram, optimized code gets de-optimized and transformed back to bytecode, and the bytecode again runs. That's the sort of slow path that it has to go through if it gets stuck, I guess. Not stuck if the assumptions fail to hold true. So let's have a look at what speculative optimization looks like in terms of our add function, right? So add function, same function. We call it in a loop 10,000 times with the same argument. I should point out one thing, the arguments don't have to be just 1 and 2. They can be any small integer, right? As long as they're a small integer, it's going to be optimized for small integers. So the first time, or the first couple times you call this function with small integers, within the feedback vector, or the feedback vector is another name for the inline cache that I was talking about for this specific function, it's going to store information about what this function is doing. And in this case, it says that there is a binary operation, i.e. an operation between two variables of signed small. So they just signed small integers, in our case 1 and 2, or just small integers that are signed. It's going to store this information within that inline cache. And over time, when it gets called multiple times, it becomes hot. The function is going to get optimized by turbofan, and it's going to be optimized specifically for small integers. If at a later point we call it with, say, floats, it's going to immediately de-optimize back to the interpreter, and the interpreter is going to have to deal with gaining new type feedback and new profiling information for a function that needs to deal with both small integers and floating point values, right? So that's essentially how this speculative optimization works. Now, this is a very simple function. Turbofan actually does a lot of different optimizations, right? So this is an example diagram. You just need to look at the second layer of this. So you can see that there's this type optimization, there's redundancy elimination, there's escape analysis, representation selection. There's like 20 other optimizations, and these are all just your generic compiler optimizations. So if you guys know it, have any background knowledge regarding compilers, if you can name one compiler optimization, turbofan probably does it, right? So again, this diagram doesn't list all of them, but essentially turbofan would perform as many optimizations as it can. It just won't on a function that is this simple, right? It just returns the addition of two important arguments. So That's it with turbofan. But before we look at the vulnerability that I wanted to look at with turbofan, we have to look at a little bit more, a couple different things. The first being shapes, right? So shapes or hidden classes or maps, whatever you want to call them. In V8, they're called either hidden classes or maps. These are used to store information regarding objects and more specifically how their properties are to be accessed, right? They also track elements kinds for arrays, which I'll explain in a little bit. It's a little harder to explain without visual pictures, right? So anyway, so shapes are created on demand as needed and shared between objects as much as possible. To show you what shapes do, I'll show you what JavaScript or what V8 would look like without shapes, right? So without shapes, if you have an object, say an object that has an X and Y value, like coordinates, for example, without shapes, the object could store the property names within the object, so X and Y, and the property names could then point to these other objects called property attributes, and the property attributes would store the values and other attributes such as writable, enumerable, configurable, etc. Now imagine you're creating a 2D game in JavaScript. I don't know why you would, but let's just imagine you are. You're going to have thousands and thousands of objects within your 2D world, and all of these objects are going to have an X and Y coordinate, right? Now, obviously, this is a waste of memory space. If all of the objects have X and Y memory spaces, you would be better off just somehow storing the fact that the X and Y, not a memory space, sorry, X and Y properties, you would be better off storing the idea that the X and Y properties can be, I'm not even going to try to explain that. I'll just go to the next slide. So in the next slide is how shapes are used. So in this case, for example, the values, the 5 and 6, are stored within the object, whereas the information about the properties are stored within the shapes, right? So this is what I was trying to explain. It's better to just store the repeatable information within a separate data structure, which is the shape or map or hidden class in this case. And what we can then do is have multiple objects share that same shape. So your thousands and thousands of objects can all point to this specific shape that has information about the X and Y properties. The shape simply says, okay, if you have an X property, it's going to be found at offset 0. If you have a Y property, it's going to be found at offset 1. So when you try to access, say, object A's X property, it's going to first look at the shape. It's going to try to find property X. It's going to look at the property information. It'll see that it's at offset 0, and then it'll access the value at object A's offset 0. So shapes are pretty complicated. I'm not going to cover like all the internal details about shapes. It would take too long, but let's have a look at what shape transitions are. So shape transitions just mean that shapes can be connected to one another in specific scenarios. So for example, in this case, we first create an empty object, then we add a property X, and then we add a property Y. What happens is the empty object first points to the empty shape. Then when you add a new property X to it, a new shape is created with just property X, and the empty object, the empty shape is then connected to this new shape that has the X property in it. And this creates a sort of transition chain, is what it's called. Again, when you add a new property Y afterwards, again, the shape X, shape X and shape Y are connected together with a transition chain. So again, what happens now, for example, if your object O now points to the final shape in that transition chain, and you try to access property X, it's going to check the final shape for property X. Again, it's not going to find it because the final shape only has property Y. And what it's going to do is it's going to look upwards or backwards through this transition chain until it finds a shape that has property X, right? And if it finds it, then it just records its offset, right? And then it just uses the offset to find the value of X in the object. If, for example, you try to access property Z, right, it doesn't exist, it's going to traverse this whole transition chain completely. It's not going to find anything, or it's not going to find a property Z because it doesn't exist, and it will just return undefined, as JavaScript generally does with most operations. So shapes can also create what's known as transition trees. And this is where things can get really complicated. Say you have two objects, or say you have an object A that starts off as an empty object and an object B that starts off as an empty object. They both point to the same empty shape, obviously. Now, say you add a property X to object A, but a property Y to object B. Now, what would happen is from the empty object, you'd have like a binary tree. Now this isn't a binary. This tree can be any level tree. I guess it doesn't have to be binary, but you would have it branch out into a shape X and a shape Y, and the objects would get their own shapes. And again, this you can sort of see how complex this can get. And because of this, this is why I say this is where vulnerabilities can lie. If for some reason the shape transition trees aren't like calculated or set out correctly, you can probably find an exploitable primitive somewhere, right? So that's how shapes work. And I also mentioned elements kinds, which are specifically used for arrays. So what elements kinds are, this is a elements kind transition tree sort of. That's not the point really. But let's have a look at the left elements kind. So you have what's known as packed SME elements or wholly SME elements. So these elements kind are reserved for arrays that only store small integers, right? So for the top one, for example, you only have 1, 2, 3, and 4, and they're all packed together, right? There are no holes in this array. Whereas for the wholly variant of it, you have holes in the array, right? You have 1, and there's holes in between, and then you have 4. So these are elements kinds. They tell the engine that this array specifically and only stores small integers. And remember, small integers are 32 bits in size. Well, 31 bits with the last bit set to 0, but 32 bits total. And the engine can then use this fact that, okay, I know that this array only stores small integers, so I can optimize accesses to indices. So the engine would know that to access element at index 2, it can just start from index 0 and add in 32 times 2, right? 64, and then just get to index 2, which would be 3 in this case. The same applies to floats or doubles in this case, except doubles are 64 bits. So again, in the same way, it would just optimize the array accesses, but instead use 64 bits this time. And finally, you have packed elements. So packed elements are any arrays that don't only contain numbers. So in my example here, I just use 1.1 with an empty object. So in this case, the 1.1 itself would also be stored as a pointer to a number object in the heap. So essentially, this sort of type of array only contains pointers, right? 32-bit compressed pointers within the compressed heap. And this array cannot be, or this array cannot be optimized for accesses, essentially. So this is like the slow type of array. If you're a JavaScript developer, you try not to create arrays like this as best as you can, because it slows down the engine and it's going to slow down your program's performance. So yeah, this is what elements kind is. It just determines or defines what values an array might be storing, and the engine uses it for optimizations. Finally, we have what's called inline caches. I mentioned this before. So inline caches are on a function level. Essentially, they're stored on functions. So inline caches store information regarding property loads and stores. Anytime an object's property is accessed within a function, the information regarding this access is stored within the function's inline cache. And this inline cache is then later on used by Turbofan to generate optimized machine code. And you'll see an example of this in the next set of slides. But there's a comic here on the right. I forgot to put a link to the person's blog that I got it from. But essentially, you can see on the left, the object is trying to access property X. It cannot find it. It doesn't know where X is, so it talks to the shape itself. The shape knows where the property X is, so it tells the object, "Hey, look, X is right here." So the object now knows that, okay, o.x is 1 because the shape told it where to find X. In this, when this happens, though, the fact that property X of this object is in that specific position or that index or that offset is stored in a function's inline cache if the function does this access. So when this when it's stored in this inline cache, if this function is called again with the same object, the object is going to remember, wait, or well, not the object, the function is going to remember, wait, I've done this before. It's not going to go through that expensive lookup process where it has to talk to the shape has to figure out where the property is, et cetera, et cetera. It's just going to look at the inline cache, which is immediately there with the function. It'll tell the object, okay, this is where the property is, this is how you access it. So that's how the object does it in a much faster way. Now, here's a better example of how inline caches work. So you have a function called getX, imports an object, and it just returns o.x, right? The object's X property. So when you call getX with an object that has the X property set to A, it has that shape. The shape tells it, the object, that the property X can be found at offset 0. For the function specifically, though, The bytecode here might look different because this screenshot is specifically for JSC, which is Safari's JavaScript engine, but I'll explain what it's doing. So get by ID lock0 arg1x is essentially going to take argument 1, which in this case is object O. It's going to access the property x, and it's going to set whatever value the property x contains into location 0, which is just like a temporary stack variable. And then finally, it's going to return log0. However, on the right, you can see two red boxes that just say NA. This is the inline cache, right? In this case, the inline cache has 2 slots. It probably has more. The screenshot just shows 2 slots because that's what's important. If you call this function once, the inline cache is going to first store the shape of this object, and secondly, it's going to store the offset at which this specific property that was accessed can be found at, right? So with this, what's going to happen is if you call this function again, the object, instead of having to go through the shape and having to look everything up, what it's going to do, or what the function is going to do, is first it's going to take that shape out of the inline cache, and it's going to check if this object shape is the same as the shape that it has stored within the inline cache. If this holds true, then it's just going to return 0 to the object, and the object just knows, hey, I can just get the value at offset 0 and return it, because that's what the function is doing, and that's what it cached from before. So this just improves performance by a large amount because you don't have to go through that expensive map lookup through the shape. So yeah, that's how inline caches are used within functions to optimize property load stores within objects. So that's enough information about turbofan and ignition. We can finally look at a vulnerability, and this is one of my favorite vulnerabilities actually, because this really showcases how unique vulnerability classes can get within V8 because of its complexity. So this vulnerability doesn't have a CVE, unfortunately, because it was found internally by Stephen Roger, I believe, through manual code review, and by Samuel Gross through fuzzing. They're both amazing security researchers that work for Google Project Zero. They're just amazing. Just go follow them on Twitter, read their blog posts on the Project Zero blog. They're amazing, right? So yeah, this is Chromium issue 944062. It's just the description is that it fails to insert map checks in array.indexOf and array.includes, and I'll explain what that means shortly. There is a great write-up by Stephen himself, called Crashing the Flow of Data. I'll release the slides after this talk. I'll just link them on the Discord, and you can grab them, and you can go to the links yourself. But yeah, this write-up essentially goes through what the vulnerability is and how to exploit it. I'll just go through what the vulnerability is because I won't have time to get to how to exploit it. But yeah, so before we get into it though, some more background information regarding turbofan is required. Otherwise, it's hard to understand the vulnerability itself. So turbofan, initially, it just takes the bytecode generated by ignition and transforms it into what's called a sea of nodes graph. And I'll show you an example of what that looks like in the next slide. But the optimizations that turbofan tries to perform are more easily done on the sea of nodes graph than on the original abstract syntax tree generated by the parser. At the end, this sea of nodes graph, after it's been optimized and whatnot, it gets lowered down into machine code for whatever specific architecture the browser is currently running on at that point in time. So yeah, this is how turbofan optimizes its code. Let's have a look at what this sea of nodes graph looks like. You don't have to understand any of the nodes here, but essentially you can see that nodes are connected with lines. There are 3 types of edges, not important. But what is important though is one node, and this node is called the check maps node, right? And this node can exist on the graph for any function. So again, I'll actually go back. This whole the graph itself is shown for one specific function, right? So this sea of nodes graph is a singular sea of nodes graph is generated for each function within your code. So a check maps node can exist on this graph. What the check maps node does is it verifies that object maps are what they are or what they should be before property accesses are done. So if you remember from before within the inline cache diagrams, remember I said that the function will first check that the object's map matches what it has stored within the inline cache before it does anything else, right? So the check maps node within the turbofan sea of nodes graph would tell the engine, yeah, I'll just get to the end, but it would tell the engine when it generates optimized machine code, it'll tell the engine that at the beginning of the optimized machine code, before any property accesses, it needs to check that the map of the whatever the function is map of whatever the function is matches whatever is stored within the inline cache of that function. Or sorry, map of whatever the object is matches the map of whatever stored in the inline cache of that function. If the map is not what the compiler expects, this causes the code to bail out back to the interpreter, and the interpreter just handles whatever case it gets. The interpreter works with anything, right? The optimized code just bails out. And the important thing to note here, though, is Turbofan, like I said, does a lot of optimizations. And one of its optimizations is that it uses any speculations that it might make to eliminate as many check maps nodes as possible. Because remember, I said if you do have check maps, now I did say that having to do map lookups through shapes are more expensive than map lookups through inline caches. Well, map lookups through inline caches are also expensive, just not as expensive as map lookups through the shape, like through the shape chain. So in a lot of cases, Turbofan will eliminate check maps nodes where it knows that no other operation might have a side effect where it might have changed this object-specific shape or map. When Turbofan does this, it will improve performance immensely because checking the map is an expensive operation that it has to do. However, if it does this incorrectly, what might happen is the object's map is changed, but there is no check maps node. Therefore, Turbofan just thinks that the map is different to what it might or what it should be, right? Or what it is. Sorry, it's different to what it is. And this results in a type confusion between two objects that have different maps, right? So Turbofan thinks this object has map A, where in reality it has map B. And map A and map B might have different ways of accessing, say, an array, right? An array is index 2, right? For example. So yeah, this might cause type confusions, which are very easily exploitable within V8. Yeah, let's just go next and let's have a look at what the vulnerability itself is. This is a lot of code. I'll explain what it is. So the vulnerable code is found in JS call reducer, reduce array index of includes. So this function essentially takes the code that exists for array.prototype.index of and array.prototype.includes, and it replaces this code with optimized machine code when it knows for a fact that the elements kind of the array that the functions or the methods index of and includes is being called on, when it knows that the elements kind of that specific array is a fast elements kind. So fast here meaning that the array only stores small integers or floating point values. When it knows this, it can replace the code with optimized machine code because it knows exactly how to access each index, as I explained before. So initially, the function node properties infer receiver maps is used to infer the map for the array. So when I mean infer, what it's going to do is it's going to, if you remember from the sea of nodes graph, every node is connected with a line. It's going to traverse up this line called the effect chain. It's going to traverse up all nodes, and it's going to try to gather as much information as it can from every node to figure out if the map of this specific array can be inferred or guessed or assumed, right, from other nodes in the effect chain, so to say. Now, at the end, the function is going to bail out back to the interpreter if it cannot find any information about this map in any of the other nodes, right? And when it bails out, no optimized machine code is generated, and it just bails out to the interpreter into the slow path. If, however, a map is found, it's going to continue with optimize. Not a map is found. If a map is found with a fast elements kind specifically, it's just going to continue with optimizing the function, right? Now, this initially looks fine, right? Like if you look at this code here, it just looks fine. It's going to check the map. If it can't infer a map, it's going to just bail out. If it can infer a map, it's going to create or generate optimized machine code for that specific map. This looks right until you look at the return value of infer receiver maps, which is the enum infer receiver maps result. And you can see the return value actually has three possible return, or the return value of the function can be three possible values. And the first one is obviously k no receiver maps, which means no receiver maps were inferred. The second one is k reliable receiver maps, which means receiver maps that were inferred can be trusted. The third one is k unreliable receiver maps, meaning receiver maps have been inferred, but they might have changed because some of the nodes from before in the graph that the infer receiver maps function uses to traverse up the graph, some of the other nodes might have side effects which could have possibly changed this array's elements kind, or this, yeah, this array is elements kind in this specific case. So yeah, so the k unreliable receiver maps tells the compiler that although the map has been inferred, it is unreliable and could have been changed by side effects of other operations. If this happens, the caller, in this case, the caller function, whatever the function is within which you're calling array.index of or array.includes, the caller must guard against possible map changes with a runtime check. And one way to do this is by inserting a check maps node into the graph. When you insert a check maps node into the graph, it's going to check to make sure that this array's map matches what it has inferred, right? If the inferred map doesn't match the map that it should, right? If the maps are different, it's going to bail out and immediately go back to the interpreter. Otherwise, it's going to continue optimizing the function, right? The vulnerability occurs because the function fails to account for the case where the map is that map that is inferred is unreliable. So I'll just go back again. So yeah, you can see on the right here, on the right, top right, if result equals node properties, k no receiver maps, return no change. That's all fine. However, it needs to also check to make sure that the result that's returned is not unreliable, right? So that's the vulnerability. The proof of concept is pretty short. It's pretty simple. I'll get into what's going on here. So initially, the function is called twice with the function f, sorry. I'll just explain what function f is doing, actually. The function f imports an index and an array. What's happening is array dot underscore underscore define setter underscore underscore is being called on whatever the index is. And when this gets called on a valid index of the array, it'll immediately cause this array's elements kind to be changed or transformed into a dictionary mode elements kind, right? That elements kind wasn't shown in that diagram that I showed before, but it says on the bottom there, it'll immediately change the array's elements kind to dictionary elements. And yeah, so that's what that's doing. And after that, it says it's going to read out of bounds, but array.includes 1, 2, 3, 4 would then read through every index of the array in order to find the value 1, 2, 3, 4, right? So initially, the function is called twice with an empty string to denote an invalid index, right? So array dot underscore underscore define setter is never called in this case. And the second argument is just an empty array, right? And empty arrays by default have a elements kind of packs me elements. So empty arrays are assumed to only store small integers. The percentage optimized function on next call is a V8 specific built-in. It doesn't exist in the browser. What it does in this case is it tells the compiler that whatever function is being called next needs to be optimized, okay? And the compiler is just going to optimize it the next time when it's called. So the final time it's called with a string. It doesn't have to be a string. It's just called with a string in this case with a very large index value and still with an empty array, right? So again, if you go back up to the function, when it's being called with that empty, initially when it's being called with the empty string, array dot underscore underscore define setter underscore underscore is not going to do anything, right? Because index is invalid. So it's not going to transition the array's elements kind to dictionary mode because the index is invalid. However, at the end, when the array is optimized and called with index, whatever that is, it's going to convert the array's elements kind to dictionary mode. However, if you remember, when the array's elements kind is transformed to dictionary mode, the map that is inferred will still be whatever the map was before because it doesn't check for that. It doesn't insert a check maps node. When this happens, it's going to cause an elements kind confusion between packs me elements, so an array that only stores small integers, and an array that only stores dictionary elements. And the problem here is that an array that only stores small integers it takes up more space than an array that only stores dictionary elements, right? So if calling array.includes or array.index of on this like a vulnerable or and all this array next will cause an out of bounds read because index of takes up more space or less space. Sorry, it takes up less space than the dictionary elements would. So yeah, so that's just how you can get an out of bounds read and write from this specific vulnerability. Again, I'm not going to go into the details of how to exploit it. If you want to know how to exploit it, just read Steven's blog post. It's very good. Goes into a lot of detail about it. But essentially, this lets you get a relative or out of bounds read and out of bounds write out of this primitive. So, okay. So yeah, the patch essentially was just to add the unreliable map check, I guess. It just checks if result equals k unreliable receiver maps. Just insert a new node into the graph. That's a check maps node that checks for the map, the receiver underscore maps argument, which is the inferred map, right? So yeah, it just inserts a check map node into the C of nodes graph, and it's just an easy fix. It's like a what 8-line, 9-line fix. It's pretty simple. But again, this sort of like shows you how unique vulnerability causes can be. Like you're never going to find a vulnerability like this in any other application. It only exists because of how complex the V8 engine or how complex the V8 engine's turbofan optimizing compiler is. Right? It tries to make assumptions. It tries to optimize machine code based on these assumptions. If the assumptions are incorrect, which they are in this case, you can get an exploitable primitive out of it. So that's it for vulnerabilities. I have 5 minutes left, so I gotta go quick. So how do you start on V8, right? This is gonna be my opinion, I guess, because this is like an end-all be-all way of getting started on V8. It's just how I did it. The first things you would start off with are, you would watch some talks like this one that explains some of the internals of V8. You can read some blog posts about it as well. That's what I did in the beginning. The next thing I did was I tried to do an easy browser exploitation CTF challenge. And I picked an easy one where it would just give you a relative out of bounds read/write primitive straight off the bat, and you would need to use it to gain code execution. I like those challenges because they force you to sort of fill in any gaps in your knowledge that you might have, because you have to understand every single bit of your exploit. Otherwise, you won't get it. You can find a write-up of that challenge on my Twitter. It should be pinned on my Twitter profile, I think. So yeah, it's a very detailed write-up. I wrote it up as best as I could. So hopefully, if you want to get into V8, you might want to give that CTF challenge a try as well. Next, what I did was I picked a very detailed write-up/bug report and decided to analyze it. And when you do this, when I say analyze, I mean, you try to look at the bug report, you look at the exploit, you try to read the code that, where the vulnerability is, you try to understand the code as best as you can. You essentially try to place yourself in the bug reporter's feet or bug reporter's shoes, sorry, and you try to understand what the vulnerability is. And when you do this, you learn a lot about the engine, right? You're reading code, you're learning a lot, right? And this helps you keep on like becoming a better researcher within V8 or within any target, really. So yeah, that's how I started. I just picked a very detailed bug report and just like went ham with it. I did this a couple times, but what you want to do is you want to slowly move on to lesser and lesser detailed bug reports, right? So bug reports that like say they only give you a proof of concept, or they only give you like you only have a patch, right? A patch to the bug, but no proof of concept. When you have this is where your knowledge is truly tested. You have to use just the code base essentially and your knowledge of the engine to figure out what the vulnerability is and how to exploit it. Obviously, when you do your analysis of these bugs, you want to also write the exploits at the same time if they're exploitable, because writing exploits is one of the best way to learn, again, how the engine works. So yeah, this is how I would go about it. After you've gone through this sort of phase, I guess, if you want to find your own vulnerabilities, I would say you take an older bug. It doesn't matter how old it is, even very old bugs can show up unless the component that they're in has been deprecated. They can show up. So what you want to do is you want to take an older bug and you want to generalize it as best as you can into a bug class, and you want to look for similar ones, right? So the example that I just gave with the Chromium issue by Stephen and Samuel Gross, the bug class itself is that there is an optimization done by the JIT compiler where the compiler makes a wrongful assumption, and you would try to look for these wrongful assumptions in the code base everywhere, right? And remember, new code is added every day, so you are likely to find one of a new vulnerability somehow through code review. If you put in enough time, code review is slow, it takes a long time, but if you put in enough time, it might work. The other alternative to this is to just fuzz everything, right? You can write fuzzes. Fuzzing is a big topic, especially within browser exploitation. So yeah, at the end, there are some useful links here. I'm running out of time here. I should probably stop. So yeah, thanks to the TuckRap team for hosting this event. Feel free to add me on the Discord and ask me any questions you might have.